right, so this is our last problem for RL circuits. Again, this is one that has two inductors in it, so we have to treat it a little bit differently, just like the one we did where we had the two capacitors. So here's our circuit. So what happens first is that the switch has been in position 1 a long time, and then it's going to close to 2. So in the beginning, then, we need to figure out how much current is flowing. So let's go ahead and draw our initial condition circuit. So for t less than 0, we're going to have the following. Oh, and I didn't tell you, I is 6 milliamps. And all of, oh, okay. Oh, and I missed one. Sorry, there's a resistor up here. Okay, so we want to know how much current is flowing at each. This looks like it's set up for current division, but we have to be a little bit careful because we have 3 branches and current division only ever works for 2. So if I wanted to find, here's I1 and I2. If I wanted to find the current I1, I could just combine these 2 other branches, right? So I'm going to combine 12 and 40. That's going to be one branch together as a parallel. And then I'll have this as my second branch. So I'm going to combine in pairs. So to find I sub 1, I'm going to combine these 2. To find I sub 2, I'm going to combine those 2. And then we're just going to use current division. All right, so again, the reason we've done this is that at DC, the inductor becomes a short. We're finding I sub L at 0 minus because I sub L is the current through the inductor is what does not change. I'm sorry, for everyone out there in the audience, I keep looking over here because there's students there. So. Okay, so I sub 1 of 0 minus, then is going to be, we're going to use current division. So 12 in parallel with 40 is one branch. That's going to be our numerator, divided by that plus the 10. So 12 in parallel with 40 over 12 in parallel with 40 plus 10 times 6 milliamps. So I get 2.88 milliamps. Sorry, there's something. Okay, and then we're going to do the same thing for I sub 2. For I sub 2, we're going to treat this as one resistance together, so 12 in parallel with 10, and then do the same process. Are we concerned that these 2 do not add to 6 milliamps? We're not, because we didn't find the current through this branch. There's one more branch, so that's okay. We don't expect those to add to 6. Okay, so this was using current division. And that requires just 2 branches at a time. Okay, so now we have the initial currents. So now we need to go ahead, we're done with our initial condition circuit. Now we need to move to our response circuit, so we're going to throw the switch. So when we throw the switch, we get the following. And that's an awfully strange looking circuit. So we have I sub 1 here and I sub 2 here. Well, what do I do with this short?
Can we take it away?
Let's think about this. All the current that's coming through here, where's it going? Is it going to go this way? No, it's going to go through the short. And all the current that's coming through here, where's it going to go? Through the short. So in some sense, I can actually pull this apart. All of this is going through the short, and all of this is going through the short, independent of each other. So I can actually pull that apart into two separate circuits. That's kind of cool. Okay, so we're gonna draw this then, two separate circuits. So two separate circuits. These are both RL circuits. We know that there is initial current through each one. Is this going to have a natural or a forced response?
Natural.
Natural response. So we automatically know that eventually these currents are going to zero. So we know it's a decaying exponential. We're going to have different LRs for each one. So we're just going to write them separately. So we have initial current. We know that for both of them, I1 of infinity is 0. I2 is also 0. Let's just call this tau 1 is going to be, what was this? This was, what's L1? 1 Henry and 10 ohms. And this is 2 Henries and 40 ohms. So L over R, 0.1. Tau 2 is going to be, should I do this right? 2 over 40, 0.05. Okay, and so now we're ready to just write the two equations. We've got initial current, final current, and tau. Okay. And so here we can use U of t because we just have before 0 and after 0. That's what U of t does. It separates before 0 is 0 and after 0 is going to be 1, so it's whatever our equation is. So finally then we will have I sub 1 of t is equal to, and here's an interesting thing. I'm not going to write it in the form, final plus how far you have to go and all of that, because I know this is a natural response. I know it's a decaying exponential. So I'm just going to jump straight to its initial value times the decaying exponential. I know that's what that is. So I'm going to do that. So initial value, 2.88 e to the minus 10t in milliamps, and I sub 2, 0.72 e to the minus 20t u of t milliamps. So again, remember what the u of t does is it says when t is less than 0, the answer is 0. So I don't have to write it as two lines of a piecewise function. And these are both natural responses because they have an initial value and they're decaying down to 0. Okay.